Okay, they give us two functions, f of x, g of x. They each have a different domain, and we're going to add and subtract and multiply and bend, fold, and mutilate these functions in various ways. Before we get into that, let's work out what these domains are because they say they're going to keep asking us about the domains. Function f, they say, is defined from 0 to 4, but not including either one of those places. So we've got an open circle at 0, and it's defined up to 4, and we get an open circle there also. So it's defined everywhere between 0 and 4, but not at either of those values. And then we have function g that they say is defined starting at -1 and including -1, and then all the way up to 5, and also including 5 because this one has square brackets on both ends. So there are our two domains. We'll probably need those in a moment. Now, function f plus g just means add the two of those up. So 3x minus 1 plus x squared minus 2x. If we combine our like terms there, we get x squared plus x minus 1. So that's f plus g. And for its domain, well, you can only have f plus g where both of them exist, meaning out here neither of them exists. Here at -1 in this little area, only function g exists. The only place they both exist is starting at 0 and going up to 4. After that, again, function f disappears and we only have function g, which is not good enough. So the domain for these is going to be simply 0 to 4. The smaller domain, in other words, where both of these functions exist at the same time. If we're subtracting them, we do f minus g. 3x minus 1 minus, remember to bracket function g because that minus is going to affect the entire expression. We get 3x minus 1 minus x squared plus 2x, which cleans up to minus x squared plus 5x minus 1, if I'm not mistaken. And the domain again is going to be 0, 4. I'm afraid we're going to get 0, 4 a lot for these functions, or these combinations that use f and g. They're all going to only work when both functions exist. G minus f just means switch the order around, so x squared minus 2x minus function f is 3x minus 1. That'll come out to x squared minus 2x minus 3x is minus 5x, and plus 1. F times g, now we get to expand. 3x minus 1 times x squared minus 2x gives 3x cubed minus 6x squared minus x squared and plus 2x, which cleans up to 3x cubed minus 7x squared plus 2x. For both of these, I'm afraid the domain is a little repetitive. It's 0 to 4 in both cases. They ask about division next, f over g of x. So 3x minus 1 over x squared minus 2x. That would be it for the quotient. Now for the domain, we'd start with 0 to 4, but there's one more thing to worry about here. Because this is a division, and they ask about domain, we have to worry about, could this ever be 0? Well, we can factor it, and factoring might clear things up a little bit. Ooh, this thing's got trouble built into it, doesn't it? This denominator will go to 0 if x is 0, so we better not allow that. X can't be 0. Also, if x equals 2, so we better forbid that as well. So our normal domain would be anything from 0 to 4. We've just found x cannot be 0. Well, that wasn't in our domain anyway, so that doesn't have any effect. The point 0 was already excluded. But now we must also exclude 2, so now we have everything from 0 to 4 except the number 2, which you'd write 0 to 2, and also 2 to 4. And these are round brackets because we can't include 2. That's the point that would blow up our expression. What if we go the other way? G over f of x squared minus 2x over 3x minus 1. Again, we would normally have the domain 0 to 4, but can we ever get division by 0 here? Yeah, we probably can. If we have 3x minus 1 equals 0, and if that is bad, then 3x equaling 1 would be bad. Therefore, if x is 1/3, that is bad. So we better take 1/3 out of our domain. You can either say x cannot be 1/3, or if you want to do this with interval notation, you'd say we can use anything from 0 up to 1/3, or you can use anything from 1/3 up to 4, but not including.